an open source method for detecting irregularities during 3D printing by comparing images of printed layers from a stationary monocular camera using Blender. Basically, Blender is an open source free physics rendering engine, and you can do a lot of cool things with this software. So by using Blender with certain rendering parameters, you can simulate a real-life environment through synthetic images to represent a real captured layer under ideal printing conditions. And further comparative analysis can reveal the location and degree of the structural deviations. Here's an example of an ideal synthetic printing process based on sliced G-code. Since a camera cannot be physically mounted parallel to the normal vector of the printing bed, perspective projection is used to produce a top view image of the print as shown. Both real and virtual cameras are calibrated using a checkerboard pattern of the same dimensions to obtain intrinsic camera parameters and distortion coefficients. Here is a sample of that. Real and virtual image comparison is based on the similarity degree of feature descriptors, shown here as a histogram of oriented gradients. So the descriptors take local image areas and turn it into a histogram that represents the orientation of shaded gradients. Pictured below are examples of what the histogram would produce based on the geometric structure captured by the camera. And here's a slide if you want to learn more about the breakdown of mathematics of how comparison of histograms is implemented. This slide goes more in depth about the comparison process if you'd like to learn more about that, but in short, every unit section of real image contains unique information from the corresponding area of the printed layer as a collection of features labeled as P. So on the left is a comparison between the real and virtual images, and on the right both are scanned and the similarities between the two is quantified in the graph, along with a heat map that is also used to help detect errors. This is another example of a 70% threshold of picking out major errors of 3 samples. Notice the change in percent of failed regions as a function of the layer it's on and underneath, in which the 3D synthetic reference is being built up layer by layer into a 3D object. Displayed here are the last set of images showing how a post-printing volumetric scan in X, Y, and Z cross-sections can detect errors. So in summary, the significance of this research will help interest towards smart 3D printing that can decide for themselves when an error has occurred and to go back and fix it.